We all know that if we have a function f of x equals the sine of x, then its graph is a smooth wave that keeps going up and down forever. But here, the problem is that the sine of x is not a simple polynomial, so we cannot easily add it, subtract it, factor it, or solve equations involving it using simple algebra. Even finding exact values becomes difficult. Like if we are asked to find the value of the sine of x when x is pi over 20 radians, then there is no simple exact answer which we can get by just plugging in the values of x. This makes the sine of x hard to work with compared to polynomials, which give exact values immediately by simply plugging in the values of x. But here is something interesting that mathematicians gradually realized over time. The Scottish mathematician James Gregory first explored infinite expansions of functions. Later, Colin Maclaurin studied these ideas systematically around the origin. And the English mathematician Brooke Taylor gave the general formula for expanding a function about any point. We will refer to them as mathematicians. They observed that complicated functions like the sine of x, when seen very close to a point, start behaving like simple polynomials, which are much easier to work with. So they asked a natural question. Can we replace a complicated function by a polynomial that behaves almost the same near a chosen point? At first, they tried the simplest thing possible, a straight line. This is what we now call a linear approximation. Near a point, the function and the tangent line touch each other, which means they have the same slope. This already gives a decent approximation, but only very close to the point. And we know that when we talk about the slope, we should think in terms of the derivatives of the function, right? So, if we try to approximate f of x, or the sine of x, with a line, say at origin or x equals 0, then we can write f of x as ax plus b, right? Which is the equation of a straight line. Now put x equals 0 here to get this. So, we get b as f of 0. Now do one thing. Differentiate on both sides of this equation with respect to x to get f prime of x here, which is nothing but the first derivative of x, or df over dx, equals the derivative of ax plus b is simply a. Now put x as 0 to get a as f prime of 0. Like for this specific case, where f of x is the sine of x, f prime of x will be the cos of x, which is the derivative of the sine of x. Now replace the values of a and b with these to get this. Oh my god. It is the first-order approximation of the Taylor series, isn't it? Great! But if instead of origin, say we want to approximate f of x at some point x equals p, then what we can do is approximate f of x, or the sine of x, as a times x minus p plus b. We do it like this, so that when x equals p, the bracket x minus p becomes 0, and the approximation automatically matches the actual value of the function at that point. Like putting x equals p, we get f of p equals this. This becomes 0, and thus f of p equals b. Then, do the same thing, differentiate to get a equals f prime of x, and put x as p to get a equals f of x, and put x as p to get a equals f prime of p. Substitute these values of a and b back into the approximation, and wow, we again arrive at the first-order Taylor approximation, but this time centered at the point p. By the way, when we do all of this specifically at the origin, meaning the point p is 0, the resulting series is called the Maclaurin series. When we do the same idea at any other point p that is not 0, it is called the Taylor series. So there is no new concept here at all. The Maclaurin series is just a special case of the Taylor series, where the expansion point happens to be 0. Okay, now the mathematicians thought, what if we want a better fit? A straight line only captures how steep the function is, but not how it bends. So they moved to the next simplest polynomial, a parabola. A parabola can bend, so now we can approximate the function f of x with a parabola at the same point x equals p, using f of x as approximately this quadratic equation. Repeat the same steps. Set x equals p. All the powers of x minus p vanish, and we are left with f of p equals c. Now differentiate both sides to get this. Then again set x equals p, where this term will vanish, and we will be left with b equals f prime of p. Now again differentiate both sides to get this. Just for future reference note, that we will write f double prime for the double derivative of f and f with n inside the bracket in the superscript like this for the n derivative of f of x with respect to x. Now again, set x equals p, and then divide by 2 to get a as f double prime of p over 2. Substitute these values of a, b, and c back into the approximation, and wow, this time we arrive at the second order, Taylor approximation of f of x. The result is a much better approximation than a straight line. But why stop at parabolas? For cubic, we can approximate f of x like this, and then repeat the same steps. Set x equals p to get d, then differentiate, and again set x equals p to get c, repeat it to get b, and then finally a. We can rewrite this 6 as 3 factorial. Substitute these values of a, b, c, and d back into the approximation, and wow, this time we arrive at the third order, Taylor approximation of f of x. This way, each time they increase the degree of the polynomial, the approximation became better and better near that point. This is how you get the factorials in the formula of Taylor series. Now, once this idea was clear, the next step felt almost unavoidable. If using higher and higher degree polynomials keeps improving the approximation, what happens if we never stop? What if we let the degree grow without bound? Take this series and write it down till infinity, which is what we call Taylor series approximation. That is what Taylor series means, and that is how it came to be. Now, if we calculate the approximation of the sign of x at x equals 0, find all the n order derivatives, and then set x equals 0. We get the approximation of the sign of x as this. This way, we can convert any complex non-polynomial function into polynomials using the Taylor series expansion. If you enjoyed this video,